Norway has invested more than $47 billion to reshape its entire coastal transportation network, a staggering figure that reflects its ambition to connect regions long divided by mountains and the sea. Amid freezing fjords and towering cliffs, this Nordic nation is quietly carrying out two of the boldest infrastructure projects on Earth: an undersea tunnel stretching for dozens of kilometers beneath millions of tons of water, and a colossal suspension bridge spanning a deep valley. These projects are more than feats of construction. They are Norway's declaration that the impossible can indeed be made real. In this video, Mandarin Tech invites you to discover how Norwegian engineers turn extreme challenges into motivation and transform the deep sea into the highway of the future. With its rugged terrain, endless chains of rocky mountains, and thousands of interwoven fjords, Norway has long faced major transportation challenges. A journey along the country's 100-kilometer western coast can take more than 20 hours, as travelers must board dozens of ferries just to reach the opposite shore. To overcome these barriers, the Nordic nation launched the E39 highway project, one of the most ambitious infrastructure programs in Europe. With a total investment of over 340 billion kroner, or roughly $30 billion. At the heart of the project lies the Rogfast Tunnel, stretching 27 kilometers long and plunging more than 329 meters below sea level, along with the Hardanger Bridge, a 1,380-meter suspension bridge connecting two steep cliffs. Once completed, these engineering marvels will transform Norway's coastal route into a seamless journey, where mountains and seas are no longer obstacles, but vital parts of a road linking the nation's future. Before construction began, Norway launched an unprecedented large-scale survey campaign. In 2016, the Norwegian Public Roads Administration signed a 111 million kroner contract with Fugro to collect environmental and geological data for the design of the bridges and subsea tunnels. Specialized survey vessels were deployed across the Vartdalsfjorden, Sulafjorden, and Halsafjorden, mapping the seafloor terrain, measuring currents, wave strength, and wind variations, while also recording meteorological data to assess the natural impact on the structures. At depths nearing 392 meters, where the Rogfast Tunnel would be built, engineers had to calculate every detail, from rock composition and fracture orientation to load-bearing capacity under immense water pressure. Meanwhile, geotechnical teams analyzed sediment layers and geological characteristics to determine the optimal locations for bridge pillars and tunnel alignments, laying the groundwork for the entire E39 route. Before reaching the world's longest undersea tunnel project, let's take a look at the Hardanger Bridge, an engineering gem spanning Norway's majestic Hardanger Fjord. Launched in the late 2000s with an investment of over $300 million, this structure not only replaced the ferry route between Boravik and Brimnes, but also ended decades of isolation for fjordside communities that had long depended on ferries amid year-round snow and icy winds. With water depths exceeding 500 meters in rugged mountain terrain, building the bridge once seemed impossible. However, after numerous wind tunnel tests, engineers chose a two-tower suspension bridge, the only solution flexible enough to withstand the harsh Nordic environment. In 2009, construction officially began, marking one of the most demanding bridge-building phases in Norway's history. The two abutments and access tunnels at the north and south end were drilled directly into solid granite cliffs, forming the bridge's signature graceful curve that hugs the valley. Each tower rises more than 201 meters high and was cast using continuous slip-form technology, a non-stop process lasting several weeks to ensure every layer of concrete fused seamlessly into a single monolithic structure. The concrete's density was constantly tested with ultrasonic sensors, while engineers carefully removed even the smallest air bubbles that could weaken its compressive strength under the immense load of the suspension cables. Once the towers were completed, massive 20,000-ton anchor blocks were embedded deep into the bedrock to hold the entire cable system in place, stretching powerfully across the icy valley below. The cable installation stage was the most demanding challenge of the entire project, requiring near-perfect precision. The two main cables, each made up of over 19,000 tightly twisted steel wires with a total weight exceeding 10,000 tons, were pulled over the towers using advanced air spinning technology. Every individual wire was threaded across the fjord through a pneumatic pulley system, floating in mid-air before being bundled into a complete cable. Throughout the months-long process, ambient temperature, cable sag, and tension were continuously monitored with laser sensors. Even a difference of just a few degrees Celsius or a minor tension error could shift the bridge deck's elevation by several centimeters, something the engineers simply could not allow to happen even once. The steel box bridge deck, 1,810 meters long and weighing 7,850 tons, was fabricated at a workshop in Eidfjord and coated with 5 layers of anti-corrosion paint to withstand sea salt and icy winds. Each segment, weighing over 250 tons, was transported by barge and hoisted onto the main cables using a self-balancing floating crane with millimeter-level precision. Once all sections were joined, engineers applied post-tensioning, installed expansion joints, and laid a special cold-resistant asphalt layer capable of flexing at 20 harshest without cracking. Temperatures around the Hardanger fjord range from 20 degrees to over 86 degrees, causing significant expansion and contraction in both steel and concrete. To handle these variations, the bridge is equipped with an automated thermal and stress monitoring system, featuring more than 20 accelerometers and 9 wind sensors that transmit real-time data directly to the Norwegian University of Science and Technology for continuous structural analysis. When it was inaugurated in 2013, the Hardanger Bridge not only became one of the longest suspension bridges in Europe, but also a living laboratory for highway engineering under extreme conditions. Here, every subtle vibration from the wind, every fluctuation in temperature, and every change in load is continuously monitored, allowing engineers to refine their technology for future infrastructure projects. Before deciding to drill directly through solid rock to build the E39 Rogfast, the world's deepest undersea tunnel, Norway had once pursued an even bolder idea: testing the submerged floating tunnel concept, a method that had proven successful in major undersea projects in Denmark, South Korea, and China. The original plan was to precast massive steel and concrete tube sections, each 200 to 250 meters long and weighing over 70,000 tons, then lower them to the fjord bed using heavy lift vessels and a self-balancing floating pontoon system. The lowering device was a specialized floating unit, custom designed for Norway's fjords, capable of maintaining stability against waves, wind, and currents while hydraulically adjusting the angle of each tube as it was lowered. During the testing phase, the equipment was remotely operated using laser and sonar positioning sensors, allowing engineers to align each section with an accuracy of less than 5 millimeters, an unprecedented level of precision in subsea tunnel construction. However, surveys revealed that the fjord's strong currents and unstable seabed created a high risk of displacement and leakage at the joints. The water pressure at depths of nearly 400 meters also far exceeded the limits of conventional rubber gaskets. As a result, after tests at Bjørnafjorden, Norway decided not to use the submerged tube method for Rogfast and instead opted to drill directly through the bedrock. The failure of the submerged tunnel experiment didn't stop Norway. It became a turning point that opened a new chapter for Nordic engineering. From that ambition, the E39 Rogfast was born, a 26.7-kilometer subsea tunnel reaching nearly 400 meters below sea level, set to become the world's longest and deepest undersea road tunnel upon completion. To bring this vision to life, engineers chose the drill and blast method, a technique Norway had mastered through hundreds of mountain tunnel projects. Automated multi-boom drilling rigs operated using 3D geological maps to pinpoint each blast location with precision. Every cycle extended the tunnel by about 5 meters, while a 1,000-ton-per-hour conveyor system carried debris out. Immediately afterward, the tunnel walls were sprayed with concrete and reinforced with steel bolts to stabilize the structure under immense water pressure. At nearly 400 meters deep, the water pressure is 40 times greater than atmospheric pressure, and internal temperatures can reach 35 degrees. The air is thick, and the drilling echoes through the rock like the heartbeat of the project. To ensure safe working conditions, engineers implemented a dual-pressure ventilation system, along with seismic and strain sensors that continuously monitor structural behavior in real time. More than 200 engineers and workers operate around the clock in 3 shifts, where time is measured by blast cycles and every drill strike reflects hours of meticulous calculation. Rogfast consists of 2 parallel tunnels connected by 39 cross passages spaced 250 meters apart, ensuring maximum safety for drivers and passengers. With a total investment exceeding $1.8 billion USD, Rogfast stands not only as the largest infrastructure project in Norway's history, but also as a symbol of Nordic ingenuity and determination. In the world of infrastructure construction, the TBM, tunnel boring machine, is seen as a symbol of modern engineering. These gigantic machines, stretching up to 150 meters long with cutting heads 17 meters in diameter and weighing thousands of tons, can bore through solid rock for tens of kilometers with millimeter precision. Each head is equipped with more than 70 tungsten carbide blades spinning continuously, consuming up to 20,000 kWh of electricity per day. TBMs have achieved engineering marvels such as the Gotthard-based tunnel in Switzerland and London's Crossrail, both built in stable, dry geological conditions. Norway's terrain, however, tells a different story. The E39 Rogfast doesn't pass through mountains, but cuts through bedrock beneath the North Sea, where powerful currents, ancient fault lines, and high-pressure groundwater pose extreme challenges. In such an environment, TBMs become vulnerable. Even a tiny leak in the pressure chamber could flood the tunnel. At depths reaching 40 bar, the pressure far exceeds the 12 to 15 bar limits of most modern TBMs. The Rogfast complex design, 2 parallel tunnels, 39 cross passages, and multiple technical and escape routes spaced every 250 meters, makes it nearly impossible for a TBM to adapt. Manufacturing and transporting a TBM would cost $100 million, requiring massive assembly space. Impossible in Norway's narrow fjords. Thus, engineers chose the drill and blast method, slower and more laborious, but far safer and infinitely more flexible. When the drilling stopped and the last rock was removed, Rogfast was still far from complete. What stood before them was only the skeleton. Its heart would beat only after passing Europe's most rigorous tests. The process began with waterproofing and pressure trials, simulating millions of tons of seawater pressing on the tunnel's 400-meter-deep arch. Next, jet fans along the ceiling were activated, capable of replacing all the air in just 3 minutes to keep CO2 levels safe. Inside, hundreds of temperature and pressure sensors recreated scenarios of fire, gas leaks, and power loss, while escape routes spaced every 200 meters led to technical corridors safely above flood level. Finally, test convoys drove through at 60 km/h to inspect lighting, cameras, and automatic response systems. Only after passing every test could Rogfast truly awaken, a symbol of Norwegian precision and steel discipline. The journey of an undersea tunnel doesn't end when the first car passes through. From that moment, a silent battle begins, a battle against time and the pressure of the ocean. Every month, Norwegian engineering teams inspect the entire concrete structure, waterproof layers and drainage systems, ensuring that not even the smallest crack or deformation goes unnoticed. Hundreds of sensors installed along the tunnel continuously measure pressure, temperature, humidity, and vibration, sending real-time data to a control center for early risk detection. At the same time, specialized maintenance vehicles regularly clean and remove sediment that accumulates on the roadway. Thanks to the combination of intelligent sensor technology and the meticulous craftsmanship of human hands, tunnels like Rogfast can safely endure beneath the sea for decades, defying the immense weight of the ocean above. From bridges stretching across deep fjords to tunnels carved beneath the sea, Norway has transformed its harsh landscape into masterpieces of engineering and human determination. The E39 project not only shortens the distance between coastal regions, but also embodies a bold vision, turning the ocean itself into the highway of the future, where mountains and seas once separated people for centuries now stand enduring works of connection and progress. Follow Mandarin Tech to continue exploring the extraordinary projects that are redefining the limits of human achievement.